floor is yours. Hello. Hello all. Thank you very much for your invitation. Evolution is a very important topic, naturally, considering the perception in popular culture in Turkey and in terms of its global position. Especially, it is a main theme in biological philosophy. That is why it is very important. In my speech today, actually it will be a rather brief speech, maybe about 10-15 minutes. I will mainly dwell on historical perspective, especially post-Darwin perspective, and the changes, and mostly I'll be speaking about the evolutional genetics and evolutional biology. And now, if I am to start, the origin of species is published in 1859, and in a couple of months, it is published with second and third editions. There are historical and scientific reasons behind that, but still, looking at the book, the work itself, of course, there are some analogies from other themes, and it emerges as a book of biology based on observations, especially. And from the evolutionary biology perspective, especially the modern perspective, maybe the first question we should ask is, what was the main transformation that Darwin triggered? So the change, the variation in natural selection, or the common origin, actually these do not originally belong to Darwin. And there is a greater depth of details that Darwin brought in. We accept that, but still, these have a very central position in terms of explaining evolution. But the main transformation that Darwin brought along is that ultimately, within a species, a group of living things, the individual variation, is actually what Charles Darwin considers as variational evolution. So the most revolutionary part of Darwin is that his views are based on individual variations and changes. And of course, there are the Mendelian, views within a theoretical perspective. So this mainly emerges as a typological perception. And it can go back to the ancient times, to Plato and Aristotle, and this is how it is perceived. The species are a sort of idea, actually, in the ancient times. But of course, the variations in individuals were considered as a degradation or corruption. So from one individual to the other, Darwin said there were individual differences. So this, he mainly focused on variation. This is a critical point in my opinion. And this is a type of living species that Darwin focuses on that was unprecedented before him. So this is not my personal opinion. This is discussed in many other sources. And if we have a closer view of the origin of species, the first chapter is about variation under domestication, and the other mainly focuses on the natural side of it. So it doesn't have a big manifesto, Darwin knows what he's doing very well, actually. He knows where he should start from and what initial view he should adopt. And of course, starting from 1890s to 1910 or 15, you know, the Darwinian evolutionary biology flourishes, and natural selection was considered to be verbal, and there was sort of a bottleneck that was felt. But without having a designer in the nature, an intellectual being without a superior mind, if life, if this is how life is formed, then it should have been put forward in a mechanical way. And there's a mathematician and biologist that have worked on this, and the birth rates and mortality rates and the Mendelian genetics were very much used on this. There is their book on that, and the evolutionary biology was then put into a dynamic framework. And around the same time, there was much emphasis on the size of the population and the related responsibilities. But consequently, all of these, through mathematical approaches, the Mendelian genetics were used, and biological trait variations were very much focused on in an attempt to explain them. And the main transformation with Darwin was that there was this crisis of the revolutionary evolution, and actually Darwin brought in a different perspective to that. And there is a much known story behind that. For instance, Angelica Dobzhansky and many others, let me think, like Stepninsky and many other field researchers who did less theoretical work, with their contribution, what happened? The classical evolutionary biology actually evolved into a modern synthesis. Yes, that is correct. But at that point, I believe that is very commonly known that there is, rather than going into the historical details, fine details, I can say I will be focusing on Theodosius Dobzhansky, and around 30s, there is his book, Genetics and the Origin of Species, which was very influential around that time. But the perspective of Dobzhansky in that book, in terms of the knowledge of evolutionary genetics, there has been a series of work, especially published in 38 for the first time, with an article. It has made its way into the literature, and for about 43 articles in a span of 8 years, this was fine-tuned and shaped by Dobzhansky, especially in terms of the genetics of natural populations. Of course, this in itself is an important series of work. And there is a semi-biographical critique of this set of work, actually. And in 1980s, there was a review as well in terms of this set of work. And the experts of genetics should definitely consider that and definitely read that, because it provides all the perspective. But what is the significance of this perspective? Because Dobzhansky, especially at a chromosome level, the changes and some morphological variations based on genetics, some researchers, especially throughout continental Europe, the relevant approaches were also integrated, and in the end, in South America, in Colombia, and in North America, from west to the tip of the state of Washington, through comprehensive sampling, the organisms that would be worked in the lab were collected, and the specific chromosomes and some variations, version changes in certain chromosomes were studied. I won't go into the further technical details, but based on a specific genetic variation, they started to do their work. The researchers tried to do their work. And physics was also used as a framework. The modern evolutionary genetics found its basis there. And if there is much focus on hereditary variations, then at a chromosome level, the structural changes were the main focus. And within chromosomes, there are some specific observations about lethality. So there are these little chromosomes and little genes that were used to study genetic variations and morphological variations and the genes causing these, the little genes, and the chromosome level structural factors were all studied here. And these are sort of the regions that set the basis for this work. And the populations are broken down to subpopulations, smaller populations, and the types of isolation and the speciation was also studied. There are different genetic backgrounds, and as a complex between the gene and its product, the interspecies relationship was very much elaborated on by Dobzhansky, and
Tamam. Ergi hocam bir dakika
in
keseceğim sizi.
hang on a
Kusura
second,
bakmayın.
Ergi.
Şimdi
We are
arkadaşlar
sorry.
uyarıyor da bu
They are
interpretation
warning
kısmı
us.
var ya şeyden çeviriyle ilgili. Onu off yapabilir misin konuşurken?
Can you turn off your interpretation,
Evet.
Ergi? Because the English
Ve,
and Turkish versions mix.
Hasan sen de konuşmayı
Hasan,
yaparken o interpretation'ı
when
off
you
yapman
are
gerekiyor.
going to speak, you have to turn off
Ama
interpretation.
off'sa dokunma.
If it's off,
Thomas,
don't touch it.
The interpretation on the right bottom, when you start giving your speech, you should turn it off. Okay, great. We can continue.
So, Fyodor Dobzhansky, speaking about him again. The genetic marker, knowledge of genetic markers. And in terms of the genetic basis, any markers that he could use to explain that, and different versions as well, and some morphological, anatomical variations and some genes causing these. He works on these through Mendelian analysis, and he also works on the lethal effects of some genes. So these variation problems were what he dwelled on. And there is this variation among species and within species. And as a result, this is a main issue of evolution. And Dobzhansky actually used this problem as a basis to study the markers, and the evolutionary biology and evolutionary genetics work in his time was actually led by his work, because his successors, Prof. and many others and their students, mainly created a school of evolutionary genetics based on Dobzhansky's work. This was supported by field work as well. That is why his work, Dobzhansky's work, is quite important. So today, in terms of speciation and the genetics of it, in any work, we still observe this theory. And there are many students of Dobzhansky that took his work one step further. So ultimately, I can say that the basis that Darwin created based on variations and based on species and categorization based on species, I mean, if there were going to be different types and categories of species, irrespective of the taxonomic levels, then there are some genetic variations that should be based on as a start. That was what Darwin said. And since Darwin, actually, the evolutionary biology could be given a fresh insight. And from 1938 to 1976, there was a series of work that I mentioned for about 40 years. And that has been a very determinant factor, I can say. And I'll stop here.
Teşekkür ederiz.
I hope I haven't talked very quickly.
Yeter, yeter. Tamam. Yani işte biraz kısaltmaya çalıştık ama zamanla
I tried to
çok da sorun
shorten it,
olmadığını
but it is
Hasan
not
Hoca'dan
possible to provide this
şimdi
information
öğrendik.
in
Daha önce
such a
öğrensek
short period
farklı bir
of
şey
time.
düşünebiliriz.
Maybe I talked about Dobzhansky. This is quite specific, but
Evet, evet.
I think you have understood
Yeah,
what
bence
I would
de.
like to talk about.
Okay, Thomas, you are next. And don't forget to make interpretation of when you are speaking. Yeah, I think that's how it works. Good.
To visit for quite some time, and now I'm sort of visiting at least, so that's a good thing. What I'm going to try to talk about, and this might be a little bit specialized because this is part of the research project that I'm starting up, is what evolutionary theory is supposed to explain and how it is explaining things. Because evolutionary theory, at least from my perspective, is a very specific sort of theory, or perhaps you couldn't even say that it's actually a theory. It's much more a theoretical framework. And it explains in different ways from more traditional theories of the sort that you find in physics or in chemistry, for instance. So the title is Connecting History and Process in the Evolutionary Sciences, and my main point will be that both history and process will have to be taken very seriously when it comes to evolutionary explanation, that they explain different kinds of things, and that only if you take history and process together, two different kinds of explanations together, that you actually get evolutionary explanations. So This is something that many biologists, I think, will agree with, but the philosophical work is to flesh out how these explanations work and what actually happens in evolutionary explanations. So this is a research project that has started up last year together with Philippe Huneman in Paris. It's called the Explanatory Scope of Generalized Darwinism. And the idea there is that you don't only find evolutionary explanations in biology itself, but there also are many areas outside of biology that try to explain their phenomena by using evolutionary thinking, evolutionary models, evolutionary approaches. So the question there is, so how do evolutionary explanations work both in biology and in areas like evolutionary economics or evolutionary social science, or even the evolution of technology, where people say, well, the production of artifacts actually is an evolutionary process. So the question there is, so if there is something in common when it comes to explaining things by applying evolutionary models, their philosophers should be able to say something more general about this. And in the background, there are a couple of worries here. And one of the worries is that if you apply evolutionary thinking outside of biology, you incur all kinds of risks. Epistemic risks, of course, because your explanation might not work, but also societal risks. And of course, we've seen those in the 20th century, things like eugenics. But also today, there are people who try to build politics on evolutionary approaches. And if you've got your theory wrong, your scientific theory wrong, then the politics that you're building on it will also be wrong. So there are societal risks that sort of are connected with this, but I won't really be talking about those today. There's also a general issue, namely, what does it take to take a theory that really works well in one area of science, namely evolutionary biology, and apply it in a completely different area of science? From one area apply in a different theory. And evolution is not unique. People also do this with physical theories. So there's an area called econophysics, where people try to analyze financial markets in terms of physical equilibrium systems. And a general question there is, well, why would that work? So this is part of the philosophical project to try to analyze that. And then there's a general issue that is internal to the philosophy of biology, namely the question, so what is an evolutionary explanation? This is a long tradition in philosophy of science to analyze how science is actually explained. There are lots of different theories about that. And at the moment, there's no satisfactory account of what an evolutionary explanation is supposed to be. So part of the philosophical project here is try to develop a good account of evolutionary explanations. So part of the problem, as I see it, is that there's too much selection in evolutionary theories and not enough history, or in evolutionary explanations, and not enough history. And here's an approach, and I'll have to shift the participants to the side because otherwise I can't see my own slide anymore. So the approach that there is a little bit too much selection, I think, in evolutionary explanations. You can find that in philosophical literature, like a paper by Alex Rosenberg, a famous philosopher of biology, who basically says, well, the main principles of Darwin's theory are not historical narratives. They're the only laws of biology, the only ceteris paribus laws of biology, and it's the application of these laws to initial conditions that generates the functional kinds, which makes the rest of biology implicitly historical. So if you know a little bit about scientific explanation, this is a very traditional model of scientific explanation. What you need for an explanation is laws of nature, and then history just provides the initial conditions, the values of the variables that you put into your laws, and your explanatory work is done by the laws of nature. And I think this severely underestimates the explanatory work that history actually does. So one of the things that is going on here is that there are a number of debates in philosophy of biology, and let me go to my slide here so that I can read it. There are a number of debates in philosophy of biology that problematize this view. So one thing, for instance, is our knowledge of history is very limited. So if you want to have historical information to put into your laws of nature, then you better have really good historical information, and typically there's not enough available. There are debates on how selection explanations actually work. So if you invoke natural selection to explain a particular factor, what are you doing? What is natural selection? Is natural selection a force of nature in the same way as gravitation? Is it a mechanism, or is it just a statistical outcome of something else? And does it not have explanatory force by itself? And there's a question, the so-called negative debate. I mean, things need to have a proper name. The negative view debate is the question, so what exactly does selection explain? Does it explain the traits of individual organisms, or does it just explain trait distributions and populations? What exactly does it explain? So there are questions on two sides. How does selection explain? How does evolution explain? And what does it explain? And then there are recent debates on the so-called extended synthesis, where people say, well, selection actually isn't that important. It's an important factor, but there are also a lot of other, for instance, developmental factors and different kinds of inheritance that also perform explanatory work. So part of the problem, as I see it, is there's a little bit too much focus on selection and a little bit too little focus on history. An example, a very classical example from biology and also from philosophy of biology, traces back to Stephen Jay Gould and Richard Lewontin, the human chin, which is a trait. I mean, everyone has a chin. Some are more pronounced than others, but there's no real explanation for why human beings have a chin. So there are these articles, we're the only animals with chins, and nobody knows why. And the question then is, so chins seem to be useless. We don't use them for anything. So what's the function? Why have they been selected? And I think this is a wrong approach, because if you look at an example like this, then you incur two explanatory risks. So the first risk is to misidentify the explanandum, so the trait that is in need of an explanation. And this is something that Gould and Lewontin, in a very famous article from 1979, have pointed out, that evolutionary biology at the time, an adaptationist program, tends to very strongly focus on individual traits. So basically you break down an organism in separate traits, and then you try to construct a selectionist explanation for each trait separately. So the trait, the chin is supposed to be a trait that evolved separately, and the question is, what made that particular trait evolve? And the risk there is, well, the chin might not actually be an organismal trait. It might just be part of another trait. So there's a completely different evolutionary story to tell there. So you can misidentify the thing that you want to explain, the phenomenon that you want to explain. And the other risk is misidentifying the explanans, which basically means that if you have an adaptive story for a particular trait like the human chin, and that adaptive story doesn't really work, that selectionist story doesn't really work, you can always come up with another one. So as Gould and Lewontin have said in their article, the range of adaptive stories is as wide as our minds are fertile. So you can always come up with another explanation of exactly the same kind. So there seems to be no end to this. So how do we deal with this, or how should biologists deal with it? Well, obviously we are taking history seriously, which is what biologists are doing. But what I'm going to argue for is that we have to take history a little bit more seriously. So first of all, one thing that I want to point out is that the two risks are interconnected. So you have this risk of misidentifying the phenomenon that you want to explain. You've got the other risk of misidentifying the explanatory factor. But the second risk actually leads to the first, because traits, organismal traits, organisms don't come as prepackaged bundles of separate traits, but you have to analyze organisms in their traits. You have to break them down into traits in relation to an explanatory project or a particular explanatory interest. So a trait, an organismal trait like the human chin, is only a trait in relation to a particular explanatory interest. So from the approach that you're taking in devising your evolutionary explanation, you actually get a particular analysis of the organism into traits. And the opposite, I think, is also true. If you misidentify your trait, then you might get stuck on a particular kind of explanation, and you might miss alternative explanations. So the risks are interconnected, and moreover, they're to be expected when studying complex functionally organized entities. So organisms, for instance, but also companies or organizations, governmental agencies, social institutions, cultural institutions, traditions, languages. Whenever you have a highly complex and functionally organized entity, you have to analyze it into its traits, and then you have to explain why these entities have the different traits that they have. And in none of these cases, except perhaps for designed artifacts, entities, complex functionally organized entities, decompose straightforwardly into discrete traits. So these risks are to be expected. They're part and parcel of the explanation of complex systems, which occurs in evolutionary biology, but also in evolutionary approaches in economics, in the social sciences, etc., etc. And this is why this is important. So how to deal with this? Take history seriously. Let me get back to Gould and Lewontin's article from 1979. What Gould and Lewontin basically said, well, in some cases, selection doesn't really do the explanatory work. What does the explanatory work is the historical constraints, the history. And for them, it was a contrast. In some cases, you have to cite selection as the explanation. In other cases, you have to cite history as the explanation. To me, this seems only part of the answer, because if you only explain with historical constraints, that seems very incomplete to me. You always also need an account of the process that actually played out within these constraints. So the point there is you need a historical explanation and you also need a process explanation. So it's not either process or history, it's always both. In biology, people know that. Evolutionary biology is a comparative science. Every biologist knows that. Traits are individuated by comparison to closely related species. So you always bring in a little bit of history by saying, well, if you look at this particular species, comparing it to the closely related species that share a common ancestor with this particular species, are there interesting differences? Are there traits in the species that I'm looking at in comparison to the other traits? So what underwrites trait individuation is homology, and this is because of the historical comparison that plays a role there. Interesting, I think, is that explanations also are comparative, but they're diachronically comparative. So what you're trying to explain is never the trait, but always the change of an ancestral trait state to the descendant trait state. And I'll explain that in a little bit more detail. So let's go back to the human chin, which is I think is a neat example. It's also an example that brings things close to home. If you want to explain why humans have a chin, then the first thing to note is humans are the only primates that have chins, which means that the chin actually is something that we have and that distinguishes us from our closest relatives. So if you compare us, the human species, with other primates, because all the other closely related species do not have that trait, presumably the state not having a chin is the ancestral state, so the state with which evolution started. So the explanandum, the phenomenon that you want to explain, is the difference between humans and closely related species, chimpanzees and bonobos, for instance. And that difference basically is the historical transition from no chin to chin in the lineage that constitutes our species, Homo sapiens. So the question that I pointed out in those articles that was on an earlier slide, why do humans have chins, is actually the wrong question. There's no point in asking why humans have chins. A better question is, well, what process caused the transition from the ancestral state, no chin, to the descendant state, chin? So adaptive explanations in evolutionary biology, but I think in evolutionary approaches more generally, so also in evolutionary economics, evolutionary social science, and things like that, concern the direction of change in a lineage. And this is something that is important to note, and it's also something that has been noted by philosophers of biology. However, so history has been taken seriously, both by biologists and by philosophers of biology. For instance, here are two very well-known philosophers of biology, Elliot Sober and Stephen Hecht-Orszag, who said, well, history comes into play in evolutionary explanations with respect to testing of adaptationist hypotheses. So very basic, their observation was, well, what is Darwinian evolution? Well, that is natural selection or other processes. There's also drift, of course, plus common descent. The two hypotheses, the hypothesis or the law of natural selection and the hypothesis of common descent, are logically independent, but they're evidentially related to each other. So you can derive evidence that helps testing one of the hypotheses from the other hypothesis. And by themselves, they're not testable. And this is basically also Gould and Lewontin's point. You cannot test an adaptationist hypothesis because if it doesn't work, well, you just tweak it a little bit until it works. You can always come up with a good adaptationist hypothesis. But what makes them testable is common descent. So what Sober and Orszag say here is that the effect of common ancestry, so the fact that species tend to have common ancestors, is that lineages begin evolving with the same heritability just as they begin evolving with the same trait value. So we, the human species, and our closest ancestors are derived from a common ancestor. So we started out in the same state, and from that same state, evolution went in different directions in different lineages, and that makes an adaptationist hypothesis testable. So recent common descent causes separated lineages to have very similar material basis for evolution, which means that the difference must be due to external factors and hence selection. So here the synchronous comparison, and I've basically already said that, is a proxy for the historical comparison. So you compare species as they are today, and that serves as a proxy for the comparison of the current state of the species with the common ancestor. So I think this is okay with respect to taking history seriously, but it's not good enough because in Sober and Orszag's view, the explanation still is done by the process part, so by the selection part. So their view that history is required to make adaptationist hypothesis testable still leaves the process part to do all the explanatory work. There's still too much selection in there. That's the view that I talked about earlier, Alex Rosenberg's view. And this doesn't fit Darwin, so a little bit of history here. Darwin himself said in The Origin that common descent is a vera causa, or rather a true cause of phenomena. And this doesn't fit Sober and Orszag's and Rosenberg's view, because in their view, common descent only is about having enough information to test the actual explanatory hypothesis, namely adaptation. So that doesn't really fit together. So my proposal is to take Darwin and take history a little bit more seriously by saying, well, the historical comparison, what does that do? Well, it determines the explanandum. So it determines what the trait is that you want to explain by means of this historical comparison. And because it does that, it should also explain why the trait is an explanandum in the first case. Why is there something to explain here? So basically, it establishes the ancestral state, and then a historical comparison also establishes how an evolutionary process from the ancestral state to the new state is possible in the first place. And why is there something to explain there? Well, evolutionary pathways have very low probabilities. The fact that we as a human species should evolve a trait like a chin is not very probable. And this is something that people who are in favor of things like creationism and intelligent design always hold against evolution when they're saying, well, it's highly improbable that a complex structure like this would come into being in the first place. So there's something to explain there, and I think the historical explanation does that. It's also important because ancestral structures basically constitute the basis for innovation. François Jacob, a French biologist in 1977, said, well, evolution is a tinkerer. It's not something that designs organisms from the start, but it basically builds on earlier structures, which are built on earlier structures, et cetera, et cetera. So the ancestral structures are very important by showing how evolutionary pathways are actually possible in the first place. And they're not just constraints. So Gould and Lewontin had something right there. They are constraints in some way, but they're not just constraints. They also open up new pathways for evolution. So they actually make certain evolutionary pathways possible and block other evolutionary pathways. So I think this is the way in which the historical explanation is supposed to work. Now, a little bit of philosophy. What kind of explanation do we have here? I think that the kind of explanation that we have here is what a philosopher of history, William Drey, in the 1950s called how possibly explanations. So this is going to be a little bit traditional philosophy of science that I'm going to talk about. So in the 1950s, in traditional philosophy of science, the dominant view of scientific explanation was the so-called deductive nomological view. What you need for a scientific explanation is a law of nature, and you need initial conditions, which basically specify the values of the variables. You put those values of the variables into the law of nature, and from that you derive a description of the phenomenon that you want to describe. That is a scientific explanation from the perspective of philosophy of science in the 1950s and the decades after that. And Dre said, well, you know, history also explains something. So this is just traditional human history, general human history. That also explains something, but obviously history doesn't have any laws of nature. So there are different kinds of scientific explanations going on in history, which are as valid and as legitimate and as important as the deductive nomological explanations that you find in the natural sciences. And he basically says, well, these explanations do something else. Traditional scientific explanations in the natural sciences explain why a certain phenomenon was necessary. And Dre said, well, historical explanations don't explain why a phenomenon was necessary, but only explain why it was possible. So here's a quotation from his book. He says, the historian need not show that what is to be explained happened necessarily in the light of the particular events and conditions mentioned in the explanation, and need not show that it happened necessarily in light of some covering law or laws. For the demand for explanation is in some contexts satisfactorily met if what happened is merely shown to have been possible. There's no need to go on to show that it was necessary as well. And I think that this is exactly what historical explanations in evolutionary biology do and in evolutionary approaches elsewhere, namely explaining why evolutionary pathways were possible in the first place. So on the top of this slide, another quotation from the same book. He says, the explanation consists in showing that in spite of appearances to the contrary, it's not an impossible one after all. And this applies to evolutionary pathways. So the criticism of evolution is often, well, it's the fact that that certain evolutionary events would occur is so improbable. So it's such an improbable theory. Well, if you've got a good historical explanation, then that historical explanation, that how possibly explanation, explains why the pathway was possible. So then basically you've done your work. So Dre had a very basic toy example from baseball. There was this radio broadcast. This is the 1950s. So there was this radio broadcast where the announcer said, "Well, there's a ball that's been hit into the far field. It's very high. It's way too high for any field player to catch the ball. However, one field player actually managed to catch the ball." And that seems to be impossible. The ball was so high, that was about 20 meters high up or 10 meters high up. No one could possibly catch that ball. And then what happened was that the announcer said, well, this seems very mysterious. However, what the player did was there was a scorekeeper's platform and there was a ladder. So the player basically climbed the ladder, got up onto the scorekeeper's platform and caught the ball. What does the explanation of this highly improbable and implausible fact? What explains that? Well, the fact that there were certain factors in place that made a particular course of events possible. So in evolution, the question would be, how could a trait or a structure, T, possibly have evolved, given that the occurrence of a complex functional entity such as T is so very improbable? And the answer is, well, the evolutionary process leading to T was possible because there existed a precursor structure, T prime, that structurally was only a small step away from T, such that a natural process was possible to transform T prime into T. So the complete evolutionary explanation, in my view, in my account, is, first of all, you have, of course, the selection explanation, so the process explanation. How did the natural process of evolution in this particular case actually play out? And then you tell the story about selection or drift or other explanatory factors that describe the process. That's a fairly traditional kind of scientific explanation. And added to that has to be a how possibly explanation, a historical explanation that complements the processual explanation and that says how the process that you've just talked about was possible in the first place. So what were the structural factors, the environmental factors in place that made evolution from an ancestral state to a descendant state possible? Okay, so I'll stop now with my last slide. I've already been talking a little bit too long. So my general idea of evolutionary explanations is that they're comparative and composite. They're comparative because you need this historical comparison between different species as the basis of your explanation. And they're composite because they're built from two different kinds of scientific explanation taken together. The process explanation that involves selection or drift, evolvability, and the historical explanation that explains how the process was possible in the first place by specifying boundary conditions that actually do explanatory work and that specify the material realizers of a population's evolvability. But this is something that I can't really talk about because I don't have the time and it would become a little bit too technical. So the basic idea is what you have in evolution is two different kinds of scientific explanation, and you have to glue them together. And the concept of evolvability, I think, is important to glue them together to get a complete evolutionary explanation. So I'll stop here, and I apologize to the translator if this was a little bit fast. So thank you.
Thank you, Thomas. That was a really good speech. Lots of ideas to think about. And I already posted my question about the possibility. I think the format is that we are going to take all the questions at the end. I'm next, so I will also have some slides. All right. Well, actually, Thomas' talk and my talk will be related, but probably not in the positive way. So we'll see. I'm going to talk about this traditional problem of autonomy of spatial sciences, and the place to start is, of course, Hilary Putnam, Jerry Fodor, and multiple realization thesis. So this thesis is used to argue that spatial sciences are autonomous, meaning that explanatory generalizations in the spatial sciences, in principle, won't be reducible to chemical or physical laws due to multiple realization. I will use those ideas to argue that there are two kinds of laws in biology. One kind involves properties that are multiply realizable, and the other kind does not. And the later, of course, I will talk about biochemical laws, and they are reducible to, as the name suggests, to chemistry. But the laws in evolutionary biology are not reducible, and the properties they involve are multiply realizable, in particular fitness. And then I will use those ideas to argue that biology owes its autonomy to evolutionary theory. That's, of course, it will be hard to translate those ideas to other spatial sciences, though, because most of them don't have their evolutionary theories. Here is the main argument. General models of evolutionary theory that contain the concept of fitness is a priori, because in these models, fitness is a genuine case of multiple realization. And two, as I said, Thomas' talk and my talk won't be positively correlated. Autonomy of a given science requires that the science in question has non-reducible laws. And the third premise, a priori laws are non-reducible to physical or chemical laws for obvious reasons, and the only non-reducible laws in biology is a priori mathematical models of evolutionary theory. Therefore, the only candidate that will make biology autonomous is evolutionary theory. So this is the main argument, and I'll try to provide argument for the premises of this argument. Well, here is the original idea. Thomas Polger and Lawrence Shapiro has this book published in 2016, the multiple realization book. They are probably the two most ambitious philosophers and the critics of multiple realization thesis. So they are close to reductionist camp than to Putnam-Fodor ideas of spatial science, their view of spatial sciences. Here is how they characterize Putnam's recipe and the basic recipe. Multiple realization occurs if and only if two or more systems are psychologically the same and neurophysiologically different. So you can extend these ideas outside of psychology, of course, for any property in the higher level sciences. We call them spatial sciences. They are multiply realized when two systems are in the higher level same, but in the lower level they have diverse realizers. They use this basic, especially Fodor, generalize this idea and use it anti-reductionism of spatial sciences. Here is Fodor's picture of the spatial sciences. You have this generalization that involve two properties in the higher level science. Let's call them F and G. You can read this as all F's are G or most F's are G, depending on the generalization, whether it's statistical or deterministic. And then the idea is this same property in the higher level can be realized by diverse physical systems. And this leads to the conclusion that those higher level laws cannot be reduced to lower level laws, because in the lower level, in the physical chemical level, there are no single laws corresponding to those higher level generalization. That's the basic idea. So the idea is that the realizers in the lower level have no common property relevant to the realization of the higher level property. Then we call it higher level property diversely realized by diverse kinds in the lower level. And why you cannot reduce this? Well, in a sense, you may, but it will be kind of unexplanatory. Lower level reduction will involve all these disjunctions, and it won't really provide better explanation than the higher level generalization. So that's the main idea. So the main thing is that higher level generalization cannot be reduced to a single lower level generalization. That's the main thing. Well, there are lots of criticisms historically. Jack Wang Kim was the first to take a critical approach to these ideas. And Ruth Millikan has a really nice paper on historical kinds and multiple realization. That's quite critical of those ideas as well. But I'm not gonna, and of course, Lawrence Shapiro has many papers and also a book, one by himself and the second one with Polger, starting from 2000. But I'm not gonna read all quotations or explain all the details. So here is the summary of the critics, the general worry about this approach to the autonomy of spatial sciences. So the first idea is that to claim that diverse lower level kinds realize the same higher level kind is implausible, because if these lower level kinds have no common property relevant to the realization of the same higher level kind, it is mysterious how those diverse kinds manage to do the job of realization. And related to this idea is that diverse lower level kinds, and this is actually approach of Jae-Kwon Kim, can only realize diverse higher level kinds. So Jae-Kwon Kim thinks that there is no reason to think that higher level kind is the same when lower level kinds are different. So there is this idea, Martian psychology, human psychology, and some ape psychology, let's say. If the realization base of all these psychologies are different, Jae-Kwon Kim thinks that you have heterogeneous science in the higher level, not a single science of psychology. That's the main idea. Existence of higher level empirical laws involving higher level properties is possible only if there is a corresponding lower level law. So these are actually different ways of saying the same idea. That's the common theme in the critics. And here is what Polgers and Shapiro do, in my opinion, in this last book, the multiple realization book, is very systematically, is to analyze very systematically what it means for a state to be multiply realized. And they come up with 4 conditions that needs to be satisfied for a state to be called as multiple realized. They say multiple realization occurs if and only if 2 or more systems perform relevantly the same function in relevantly different ways. This relevantly is the key here in their approach. So they explain this definition as follows. P is multiply realized F. P is here in the lower level science and F in the higher level science, if and only if 1, F is classified as a single kind in at least some models of higher level science. And I want to just direct your attention to this language. Before, no one actually talks about this in a science. So they look at the scientific practice to determine whether something classifies as single kind or not, rather than philosophical ideas. That's important in their approach. P's are classified as different kinds in at least some models of lower level science. And 3, P's are classified as different kinds in those models of lower level science with respect to the causal powers relevant to the performance F. And 4, variations among P's are distinct from the variations among things that are classified as F kind at the higher level science. All these conditions aim to clarify this multiple realizability thesis. Because people say, for example, that since some sequences in genes differ from each other, those genes are different kind of realization, the same properties. But according to these conditions, they won't count as different kinds in the lower level science. Okay. Now I apply these conditions to different kinds of properties in biology, which occur in different kinds of laws in biology. The first one, what I will call laws in evolutionary biology, and my example here is fitness. Well, let's look at the definition of fitness and principle of natural selection. These are quotes from Sober. Trait X is fitter than trait Y if and only if X has a higher probability of survival and or a greater expectation of reproductive success than Y. And given this definition, here is the formulation of nature selection, if A is fitter than B in a population in which no other evolutionary causes are at work and the traits are perfectly heritable, then A will, in expectation, increase in frequency. I will say that this generalization principle that is supposed to apply all biological populations is a priori, and this is kind of course, obvious given the definition of fitness. And also the property fitness that occur in here and gene frequencies are both multiply realizable. In the sense, Holger and Shapiro defined that concept. So why? Well, organisms with the same viability fitness, let's say, 0.6 fitness value, may have quite distinct physical properties. For example, an ant trait may have viability fitness value of 0.9 and a human trait may have viability fitness value of 0.9. The same goes for fertility fitness as well. In the same way, we can say that trait frequencies are also multiply realizable. So the question is whether fitness satisfy Holger's and Shapiro's conditions for multiple realizability. Well, fitness in the general model of principle of natural selection is treated as a single kind. So the first condition is satisfied. We are going to look at the science whether that kind is considered to be classified as a single kind. Properties of organisms and the environment that fitness supervene on are treated as different kinds in many models of lower level sciences. That condition is also satisfied. It is also true that differences in the lower level kinds are relevant to their realization of fitness in the higher level science. Finally, differences among the lower level kinds are not merely reflection of the intra-kind differences among the same fitness values in the higher level science model. So I kind of think that it is obvious that fitness satisfies those conditions. And I also argue that multiple realizability is the reason principle of nature selection is a priori. Why? Because since fitness and trait frequencies satisfy the conditions of being a genuine case of multiple realizability, the general models of principle of nature selection turns out to be a priori, because once the fitness and trait frequencies are stripped away from all the physical details, the model merely relates numbers. Otherwise, the model would not have been a priori. That's and general model is here is important. You'll see why in a minute. All right, so here is the summary so far. If a higher level generalization contains kinds that are genuine cases of MR, multiple realizability, then the law that relates these kinds turn out to be a priori. We may then say that kinds that an a priori law contains are not really empirical kinds. Perhaps we can call them mathematical kinds. I mean, this is up for philosophical discussion, but my argument doesn't depend on how you interpret them. My argument only depends on the scientific practice that fitness in the practice of evolutionary biology is classified as single kind. So that's the key assumption, I will say so far. Possible objection. Marcel Weber has a very nice paper on multiple realizability and laws in evolutionary biology. This is a direct quote from his paper. Fitness differences between certain phenotypic variants are explainable in terms of physiology, biochemistry, or ecophysiology. I have argued that some of these explanations are not merely case by case, but have a greater scope. In many optimality models, for instance, fitness is shown to be a function of energy efficiency of certain processes or behaviors. Thus, a connection is established between fitness and a physical quantity, or between biological concept and a physical concept. So he seems to suggest that the fact that biological systems are multiply realizable, that's not an obstacle for biology to have laws, even in evolutionary biology, empirical laws he has in mind though. Well, what he says absolutely correct, but kind of it doesn't undermine what I have said so far. Weber's claim that fitness differences are explainable in terms of physiology, biochemistry, or ecophysiology is of course true. But these explanations will have to be limited to local environments and populations that live in those environments. So this is kind of Jae-Kwang Kim's picture of spatial sciences. He thinks that when there are empirical laws in the higher level, then they are reduced. So he agrees that there can be species specific laws, but then those laws will be reducible to chemical and physical laws. So it is true that we can formulate the following kind of conditional laws. In an environment with certain features, if members of a population have this and that physiology, etc., they will have such and such fitness values. Correct. Weber realizes that such laws will be local, since there are no general explanations of fitness values in terms of the same physiology, biochemistry, etc., for all fitness assignments in all populations. So when I talk about general models, that's why I said general model is here important, like principle of natural selection that aim to apply all populations. Then you don't have a single biochemical or physiological explanation of these fitness values. For each you do, but you can't unite them by a single explanation. Thus, to the extent that fitness values are explainable in this way, these models we have will be empirical but limited in scope. To the extent that we have general models like PNS, that contain fitness assignments, these fitness assignments are not universally explainable in terms of the same physiological, biochemical, or ecophysiological properties. Of course, each one will be explainable locally, but not globally. Well, here is the picture, and following Fodor's diagrammatic representation, we can say these are here traits in different species. You can, well, this is like human, maybe this is bat, and X is something else. So each of these fitness assignments, as Weber says, will be explainable by some physiological or ecophysiological or biochemical properties in the lower level. But you will have these biconditional laws, so they will be reducible. What you won't have is relating bridge laws to this higher level generalization, which I call general models of evolutionary theory. And this is something I pick up from Ruth Millikan's idea, although she is critical of it. I don't think she realized the implications of what she has actually identified here. She said you can only have definitional relations among these, which is correct. That's why we have a priori laws in evolutionary biology. So all these diverse higher level kinds are related by some definition. And that's what happens in the case of general models. We don't have empirical biconditional laws here, bridge laws, in this second stage. Definition of fitness subsumes all cases of T sub fx under a single mathematical kind, and same goes for trait frequencies. So thus, we have an a priori law at the higher level science, evolutionary theory, that cannot be reduced to any lower level empirical law, since among lower level kinds realizing F, there is no common property relevant to the realization of F, and among lower level kinds realizing G, there is no common property relevant to the realization of G. Well, this is the first part of my talk, and the second part is not all laws are a priori, and not all laws are non-reducible, to physical and chemical laws. To say that general models of evolutionary theory that contain fitness are a priori does not say anything about the rest of biology. Biochemistry is a science with the aim of explaining biological properties in terms of chemical properties on which these biological properties supervene. Given this, it is reasonable to look at biochemistry to find empirical laws in the higher level science that are reducible to lower level chemical laws. Well, here is a quote from biologists, an example of reducible laws. Included in the 10,000 protein structures now known are several families within which the molecules maintain the same basic folding pattern over ranges of sequence homology from near identity down to below 20%. How is structure maintained in the face of such drastic sequence change? The answer is that the structural details are not maintained. Rather, it is function on which selection is acting. In both closely and distantly related proteins, the general response to mutation is conformational change. Variations in conformation in families of homologous proteins that retain a common function reveal how the structures accommodate changes in amino acid sequence. Residues, it is this part that's critical for my argument, active in function are resistant to mutation because changing them would interfere explicitly and directly with function. So what we have here, what seems to be a case of multiple realization is not really a case of multiple realization, because there is a key part of the sequence with which if you interfere with it, then you don't get the same function. So this is an example of reducible property. Well, does this case satisfy the condition of Polger's and Shapiro's multiple realizability thesis? These protein families cannot be grouped as diverse kinds with respect to the function they perform, since they share common sequences that are active in function. This example satisfies Polger's and Shapiro's first two conditions, but it fails to satisfy their third condition. It does not satisfy the third condition because the problems that retain a common function are not grouped as diverse kinds with respect to the causal powers relevant to performing the function in question. If we have conditional laws at the higher level where the function in question is in the antecedent and its biological consequence is in the consequent, then such laws can be reduced to a single lower level law due to the fact that we will have bridge laws relating lower level kinds to higher level kinds. So here is the picture here. We have different picture with respect to the second kind of biological properties. Now we have these biconditional laws. We have empirical and causal spatial science laws in the higher level science. And through these biconditional laws, they can be reduced to a single kind. These, what seems to be different kinds here, like P1 to Pn and P'1 to Pn, are not really different kinds with respect to the function they realize. So we have this common element. Here, let's call it P star, and here, let's call it P2 star. Then we have a single law in the lower level science, which is empirical and causal. That means we can reduce higher level properties, but higher level generalizations to a single lower level law. Okay, and I believe this is sort of like, I'm going to repeat the argument I started with in the beginning of my talk. This shows that if biology is autonomous, that autonomy is due to evolutionary theory, because other kinds of biological laws are reducible to chemical and physical laws. So here is the argument again. Any given branch of science is purely autonomous if it contains non-reducible laws to lower level sciences. As I said, this is the most controversial thesis, for which I didn't provide an argument, actually. That's the only premise I didn't provide an argument, by the way. But historically, that was the idea of Putnam and Fodor. In biology, genuine cases of multiple realizability involve fitness that figures in the general models of evolutionary theory, and these models turn out to be a priori. A priori laws cannot be reduced to physical or chemical laws. Biochemistry tries to understand biological function in terms of chemical processes, and in these cases, properties high-level empirical generalizations contain are not genuine cases of multiple realization, and therefore, these generalizations are reducible to lower-level laws. A priori laws biology contains come from evolutionary theory. Therefore, biology can derive its autonomy only from evolutionary theory. Thank you. And I will stop screen share. Why cannot stop this? Okay. I'm done. Hasan, you are next. Does everybody hear me?
Yeah, we can hear you. No problem. No problem. Thank you for giving me the floor. First of all, thank you very much for inviting me to this session. Of course, there is lots of technical knowledge in our presentation, so my presentation will be softer, and I hope that I'll make a speech that is not technical. And I will look at it from the perspective of a philosophy historian. So I will try to look at this issue from the perspective of culture. My main subject is that there are some circles that are against the evolution, and there are some questions asked to us in this context. I'll try to make an analysis in this sense, and I will try to prioritize philosophical views, and I will also convey my personal views. Generally speaking, in such debates, we see lots of important problematic areas, including the relation between science and religion. So this can be considered as the problem of religion and science. The most important claim is that the evolutionary theory is against the idea of a single God dictated by religions. This claim is specified in detail in the holy books, and this is the product of epistemologically seeing religious men same as philosophers. So there's an argument in that light. Is it correct? So religions specify that the world was created by God. in daily speaking, it is quite similar to the fact that Fatih has made this table, created this table. It's no different. So holy books of these religions are made of soil, smoke, water, or something else. Even if we accept the creation of something from nothing, it is not easy for human intellect to understand it. Even if we accept it, the consequence doesn't change. Even if we accept this notion, we can also discuss whether nothing is something or not. And it is already discussed. Creating from scratch or nothing is not explaining how did we have this world. So the thing Mehmet has created this table doesn't give any explanation to this process. If we say that the God created the universe in 6 days from nothing or scratch, doesn't give any explanation to this argument. Or there are different arguments stating that the God created people and individuals as well as the universe in gradual steps, but there's no explanation to this argument. I believe that it cannot be explained. There are some religious texts referring to holy powers, so they don't have any such explanation. They just emphasize on the greatness of God, and they do not question to these views, and they are subservient to these views. Let's say that Mehmet has created the table from different materials, such as stone or wood, doesn't give any explanation to the variability of materials. It doesn't explain any phenomenon, and it is not effective in sorting out the problems in practical life. For example, let's say that the God has created cancer. It doesn't give any explanation to the creation or evolution of cancerous cells. The same thing applies to historical processes. A historian may try to explain human history through the creations of God. It is so nonsense. And we cannot also state that the God has created all processes. We cannot bring an explanation to that. So within the historical process, how did the universe emerge? How did individuals or organisms emerge? We need to answer these questions. For example, the evolutionary theory is trying to explain this process through different processes such as selection. Independently of the interpretations of people, there is no religion. People give meaning to religions. They internalize those religious views. Their conditions, their wishes and requests are decisive for the emergence of these religious views. As for the argument that if there is a religious text, there is an interpretation in place, and there are also some differences between different sects and religions, and it is supported, this argument is supported by these differences. I believe that religious perceptions and interpretations are obstacles for the generation of scientific knowledge. I would also like to say that the understanding and interpretation of holy texts requires the perspective of a historian, because texts are created within the language which is constantly changing. In before Christ 1200, some texts were created but it is really difficult to understand and interpret them in our current conditions. So we need to consider the use of language in that period while thinking about those texts. So we are trying to interpret religious texts continuously by the use of postmodernism, but this is not academic. When you look at these texts, you see that these texts are anthropomorphist texts. For example, it is stated that the God created the sky with a holy light. We have such narrative. If we see them as metaphors, then it brings us a new problem. The depictive narratives cannot be compared with science or scientific views. If you ask me, this can be considered as scientific thinking. My second argument is that evolutionary thinking rejects traditional thinking. So it brings an evolutionary approach on people, organisms, according to those who are against these thinking. These people are thinking that there are differences between organisms and individuals. There are differences between individuals and animals. They state that individuals have the ability of acting independently. These plant behaviors causes different kinds of behaviors. For example, mice make their nests underground, and some animals do act differently. Maybe we cannot see any plant action from plants, but when you closely approach them, you see that there are some plant explanations. It is possible to monitor them. For example, plants actually instill their roots into the soil in order to have access to food they need. So such plant actions seem to be related to the protection of the relevant organism or entity. The effectiveness of organism is based on some plants. These course observation led to the creation of evolutionary approach. So there must be a causal relation between the emergence of something and the processes that lead to the emergence of that organism. Animate and inanimate objects are also created by God according to the thinkers, and they state that they try to explain why people act in a certain way. Spinoza tries to reveal the causal relation between the action and the process that brings a certain individual to act in a certain way. There are some wishes that lead to this process. Spinoza brings two conclusions. Firstly, people are free and have some options, but they are not informed about the reasons for why they are directed to a certain cause. Secondly, people take action in line with their aims. And in the light of these conclusions, Spinoza says that people only look at the root causes of the events and they get comfort when they think that these are caused by external factors. According to Spinoza, let's say that they haven't found any root cause, then they must turn to themselves. Then they need to identify which aims force them to act in a certain way. So they focus on their creation and they generate ideas on the creation of other creatures. So while investigating these issues, they discover lots of tools. For example, eyes for seeing, teeth for chewing, plants for eating something, and the sun giving the light. So these are the things that serve to their needs. So when they find these tools available, then they force them to believe in something else, an entity which is holy. Therefore, they create some tools for certain aims. They think that nature is free and nature must have a manager or director that is directing all processes for individuals. That's the view expressed by these people. And they give a character to the God, and then they create a God that is dominant over individuals. Then they direct everything in line with the interests of individuals. According to Spinoza, each individual creates a God for himself or herself and wants the God to love himself or him or her more than anyone else. So this belief is seen embedded in the human spirit. That's why this prejudice is highly discussed in our circles. So individuals look for ways to identify why we are created, why everything is created. They couldn't find any reason for floods. And they say that they make the God angry, that's why floods occur. So they have some experience from their daily life, and it is saying the opposite to them. And many examples show that these floods may also occur to believers. They try to provide a holy reason for all natural disasters. This is easy for them. So rather than eradicating the system and establishing a new one, they are actually illiterate and they continue to live in this way. So the judgments of God are very decisive for them, and they think that these judgments are superior to those of individuals. So according to Spinoza, these arguments implies that the nature doesn't have any aim and it's the imagination of people. When we look at the ideas for root causes as specified by Spinoza, of course, we cannot say that a thought is wrong just because it's emerged out of imagination. If we can prove that it is correct, then it can be considered as correct. But in causal relation, there is an important problem, and Spinoza says that causality renders the consequence into the cause. So causal relation is decisive for the consequence. For example, when we hit the ball with a billiard stick, then the ball is moving. But the causal relation is embedded in both the cause and the consequence. For example, the wind is actually blowing and the branches of trees are swinging. But according to some people, the branches of trees are swinging and the wind is blowing. This is not correct. So when human beings are the case, we can say that we cannot say that our current actions are always decisive for consequences, but our plans for the future are effective on our current activities and actions. When we change our plans, we can change our actions. For example, when we remove a sapling from the ground, then we can change the future and we can prevent it from growing and turning into a tree. So it is also claimed that the future is created by now and it is philosophically problematic. And according to some philosophers, the causal relation may have a value in understanding organisms or individuals, but they say that we cannot apply to our lives. In that sense, it's necessary to say that it has a negative aspect. So it is logically strange that the consequence is decisive for the cause. It is really nonsense to say that. Are we using our eyes to see, or is it our eyes created for surviving? So why do we have a night? To have some rest or for some other purpose? So applying a meaning to inanimate subjects is also strange. So we have organs such as eyes, hands, heart, but all of them are coming together to create the body. So we have to think them in an integrated way. We can separately think of the functions of the sun, sky, or some other entities, but we have to consider them in an integrated way. All godly creations or holy creations are problematic in terms of scientific thinking. In classical godly creations, an aim is sought in the universe. There is no causal relation for God, and if that is the case, then it is quite nonsense. So we cannot say that God has given us some aims and causes. So we have to get rid of these ideas and we have to guide ourselves towards scientific thinking. Alaaddin Şenel has created an approach based on Kandinsky, causal relation is providing us a space where we can see a causal relation in the universe. In inanimate world, there is causal relation, but in biosphere, we have functionality as well as causal relation. Therefore, causal relation and functionality as well as the relations between symbols must be taken into consideration in that sense. This phenomenon is a differentiating factor for human beings. So we have an anthropological time schedule, and we think that it is decisive for the future. In geosphere at biological and chemical level, we can think of some perceptions and phenomena, and these are directed by causal relations. In cultural world, we can explain everything by causal relations. So providing a causal relation to the universe is including the universe in the world of intellect. And as I have said before, it is quite nonsense. There's a third argument. So it is argued that evolutionary theory is based on arbitrariness, but it is totally incorrect. So evolution takes into consideration some observations that are made. So the possibility of the evolutionary theory being an arbitrary thing is impossible. Causal relation is quite nonsense in this sense. Reinhardt explains this issue in this way. There are some pebbles by the sea. A person can think that they are scattered within an order, but water is actually scattering them through the movements of water. There are some arrangements in the distribution of pebbles. It seems that a person is or an entity is arranging these pebbles in a certain way. So we don't have to adopt an anthropological thinking because there are some natural events and distance incidents that cause these phenomena. For example, waves are important in this sense. Actually, the impacts of individual waves is not dependent on a certain arrangement or order, and no one can know when a pebble will end up at the end of a wave. A wave could be large, a wave could be not large, and there could be differences in the distribution of these pebbles depending on the size of the wave and movement of the wave. So the apparent causal relation of organisms cannot be explained by some godly creations, but it can be explained by the views of Darwin. For example, Greek philosopher Empedocles says that organisms grow up from the ground. For example, arms and legs occur or are created spontaneously, then they organize themselves when they all are created. If a good thought is explained in an insufficient framework of thinking, then it is forgotten. Darwin's scientific thinking and his scientific genius have explained evolutionary theory in a new perspective. As you know, Darwin's scientific work and its scope must be taken into consideration. A theory was explained by Wallace, but the theory of Darwin is explained because Wallace and his scientific work are not as strong as that of Darwin. While classifying the species, he actually couldn't give a systematic explanation of the things he covered in his study. So according to Darwin, we have a pyramid. At the upper side, we have human beings, then we have monkeys, reptiles, fish, and so on. Darwin's approach brings into account the luck or coincidence, but through adaptation, he explains these behaviors and phenomena. This approach is also based on empirical views, and it gives an explanation to nature. Now let's look at the fourth argument. The universe can be explained by observation. This is an argument, but this is not correct. Let's talk about a mayfly which lives for 1 day. This fly is trying to explain the behaviors of individuals only in 1 day. So it is impossible for this fly to observe everything. So if one of these flies had been Darwin, then he couldn't bring into account this theory. So the sequences of time show that this fly is luckier than us, and a human being's life is 80 years, but the life of a human being is shorter than that of the fly in terms of explaining the phenomenon introduced in their lives. Actually, evolution has a historical perspective, and it is based on a historical epidemiology. Evolution theory cannot be directly tested. It is another argument, but geology, paleontology, and genetics, what can we do about their findings? There are some different fossil types, but their development is quite different. Paleontological evidence shows the development of human evolution, and there is some data that can be used for bridging the gaps or bridging the loopholes. So we have to explain this data. Then it is possible to say that indirect data or empirical data needs to be explained based on a theoretical approach, and this theoretical approach is quite clear in terms of the evolutionary theory. So why is evolution? Why is life going to some more developed states? So is evolution a causal relation for generating the upper superior human beings? We can also think about that. It is another argument. The great contribution Darwin comes into play here. Darwin explains the process of evolution based on some theories, and theology is totally eliminated in this process. And he tried to explain these processes with adaptation. And in terms of creating new hypotheses, it is functionally used. The last argument is as follows. Evolution is still a theory and it hasn't turned into scientific school. This is absurd. Theory is observing, looking, monitoring according to the definition of the term. In terms of scientific thinking, theory is explaining certain concepts to establish systems. Creating such a conceptual system requires great scientific thinking at the highest level. In epistemological terms, theory is considered a conceptual thinking. It is also considered as phenomenon and hypothesis, and they can be confused with each other. Evolution is only a theory according to these arguments. Yes, it's a theory, but it is substantiated by evidence. Theory, assumption, and hypothesis are different things. Assumption is generated based on an idea. Hypothesis is put forth to prove an idea. Theory is generally substantiated by a set of hypotheses. So the word of theory is quite lean in this sense. And theory is not a philosophical worldview. Theory is related to a certain phenomenon, but philosophical worldview may encompass the entire world. It may be composed of emotions, judgments, values. In that sense, theories do not consist of personal views and judgments. Theories can also be tested with their peers, and theories are compared with each other, and one theory could be better from another one in terms of clarity and other factors. In that sense, they can be compared with each other at certain levels. There are differences in terms of hypotheses, laws, and theories, and there is no hierarchy between them. When a theory is proven, it doesn't turn into a law. For example, the mole law is explaining a causal relation between certain factors, but theories are the explanations of phenomena. The apple is sweet. The wood doesn't fall under the water. And these are some phenomena, and theories are explaining them. If we do not have any theory, we don't have any explanation. That's why it is not good to eliminate theories. Such an attitude would reduce science into an unimportant field. The success and achievements of science are based on explanations and theories. The physics is based on the atomic theory. If we ignore the atomic theory, there is no science as physics. This is also valid for evolution and other fields because it's the reflection of biology. There is no doubt that in addition to these factors, there are also many factors that can be put forth, but I have just chosen the theories that are philosophically compared and discussed. This theory is also debated by the extremists and religious people. there are some people who reject the change continuously, and this fixed world is given by God to us. This is such a worldview, and they try to dominate over this world through this worldview. And this is my final word. These people are scared of change, and they think that changes are not good, and changes are unreligious in Islam culture. This is the view of the religious and extremist people against the view of evolution. That is the end of my presentation. Thank you.
Teşekkür ederiz Hasan Hocam.
Thank you, Hasan.
Zevkle dinledik.
We enjoyed listening to you.
Evet,
Okay,
bitti.
so our
Soru
presentations are
alabiliriz.
over. We can get questions if there are any.
Bunu herhalde chat üzerinden.
I believe the questions will be written. Yes, in the chat box there is.
Ha onu
There's one
ben
for Thomas.
sormuştum zaten.
That was my question
Chat-
indeed, Hasan. I wrote that question. Okay, okay.
The question is, how can we determine something to be possible without knowing what is necessary? I mean, these are two model concepts related. And if we say the goal of explanation in history or in historical sciences is just to give an account of how is it possible, I would think there is something missing here. We should have some understanding of what is necessary. And I just thought that evolutionary theory provides those what is necessary through a priori mathematical models.
Yeah, I think that is actually a very good point. So the idea of how possibly explanations, which I took from Dre, is basically a contrast with the how necessary explanations in the natural sciences. And Dre basically just said, well, the how possibly explanations just have a different explanatory aim, right? They just want to show how a particular line of events is possible. And I think you're right that in order to determine how a particular line of events is possible, you also have to have basically some understanding of the laws of nature, but that understanding is sort of in the background, right? So Dre's example was of the baseball player that climbed the ladder and got onto a platform, and that enabled him to catch the ball. The most important explanatory factor is the fact that there was a platform and a ladder there. So that's just a historical fact. But in the background, of course, there's all kinds of knowledge about what is possible and what is not possible for human beings. How high can human beings climb? How fast can human beings climb a ladder? And those are all the necessities that stand in the background. So I think this is not really in Dre's work, but I think a good interpretation would be an interpretation of emphasis. So the how possibly explanation explains possibilities by placing emphasis on historical circumstances with all sorts of other knowledge in the background. And conversely, the how necessary explanations, so the sort of the standard law-based explanations in the natural sciences, explain how a certain event was necessary, but it was only necessary given certain initial conditions. So the historical conditions stand in the background there. So they do play a role. I mean, clearly in deductive nomological explanations, laws do the explanatory work and historical conditions play a role. And you can say in how possibly explanations, the historical conditions do the explanatory work, but the laws of nature and the whatever it is that determines necessities in the universe also plays a role in the background. It's sort of the boundary conditions of the how possibly explanation. So I do think you're right. You have to know it both. But the question is, what is the factor that does the explanatory work? And what are the additional factors in the background?
Okay, well, just one moment. I don't want to take the other people's time, but yeah, the emphasis I think maybe the difference is the emphasis, but I don't think they have to be contrasted. So in a way, the background is also part of explanation. This is sort of Hempel's point, right, against the critics. That, well, yeah, you have explanatory sketches, but they are incomplete. The ideal explanation will include both, maybe. And I'll stop.
Okay. No, I think you're right, but it is a little bit a question about the work that is done, right? What actually does the explanation? So what answers the question, why is this outcome necessary? And what is just part of the question without actually providing the answer? And I think for Dre, the most important thing is that there's just a different question. The question is, what, for Dre and how possibly explanations, the question, what makes this outcome possible? And the most important factor there is, well, you've got something to start with. You've got a structure to start with. That is what makes the trajectory possible in the first place, but it doesn't actually have to occur. So it's two different explanatory targets. And I suppose, I mean, you could probably read Hempel in that respect. I personally wouldn't, but it's a possible interpretation, I suppose.
Thank you. Well, there is, oh, by the way, I said you can write your questions in the chat part, but that's not correct. Apparently, I was warned, and so you direct your questions in Q&A. There is an option in the bottom, Q&A. So if you have questions, you can write your questions in the Q&A part. And there is one question. I don't know if you can see this, Thomas. You probably can, right?
Yeah,
and that question is to you as well.
Yeah, I see the question both in the chat box and in the Q&A. So how would I differentiate between how possibly and how actually explanations in science? Thank you. That's a good question. The basic distinction would be between the historical explanation, which is how possibly, and the process explanation, which is how actually. So the process explanation, a fairly standard selection explanation in evolution, would tell you how the process actually occurred, given that at some point there was an initial starting state. How did the process from that state towards the end state actually occur? That is what the how actually explanation does. And for that, you need perhaps laws of nature, perhaps mechanisms will do, but you need something of the sort that you find generally in the natural sciences. So the sort of explanation that you find in physics, how does this process work? That is the how actual explanation, and the how possibly explanation is, so what were the conditions that make the occurrence of this process possible? Whether or not it actually occurred is another question. So what was the situation that made a trajectory like this possible? So the main differentiation basically is that the how possibly explanation is deeply historical, and the how actual explanation is an account of the process, and it's a more general explanation. So how actually processes are repeatable, whereas historical conditions are unique. That would be sort of the way in which I would differentiate between the two. I hope that answers the question. I hope that that is more or less clear.
Hasan Hocam, Q&A'deki sorulardan
Hasan,
biri
are you
sana
there?
Galiba.
One of the questions actually is for you in the Q&A box. Hasan?
Hasan Hocam şu anda.
I think, oh, you're there. Okay. I saw the question. The only thing I can say is that as an assumption, metaphysics is says there's a reality that is waiting for us out there. But it's sort of a mysterious background assumption. So this is the first point I'd like to raise. The second one is that it feels like the real truth, the real world that is waiting over there, or the external world, you may call it, that is a fate, an instinctive one, and it feels like I'm having a hallucination, and I don't think that the computer that is in front of my eyes is just a hallucination. That is not real for me. Of course, we can be critical to that. I don't disagree with postmodernists in all aspects, actually. And in terms of subjective reality, based on religion, in terms of language, or a cognitive process, yes, we can adopt a perspective, but it doesn't mean that there is no other world that other than mine. So we can say that from a philosophical point of view, no matter what we discuss, scientists are not like philosophers. So they are unlike philosophers in terms of evolution. In every symposium that I attend, when I listen to scientists, they say, this is true. If you don't believe it, then just prove it. So they always refer to the correspondence theory. So this means that, yes, it appears that, as I said before, we human beings are living in a culture, we're getting socialized, we're using language, and we have a personal background. That is correct. But the point that I disagree with postmodernists is that they disagree with dichotomies, as you know, and they also disagree with subject-object dichotomy. And my personal views and behaviors can be handled within subject-object by conditionality. And more importantly, I can self-reflect, and sometimes I can see that I'm wrong. And usually it's the facts that show me that I was wrong. So being totally constructive, socially constructive, mainly adopting this, or solely, exclusively adopting this, is actually not an explanation to why I have been wrong. So these are postmodernist hypotheses, and they are debated and discussed frequently, but they don't change the efficiency and effectiveness of scientists, because this science is a tradition and it is well established, settled. And, you know, negating or verifying, these are different things. Of course, there are hypotheses, and they usually test them, and just verifying them or negating them, it's not like that. We cannot just reduce it to that. As Popper said, a thesis or a theory by a scientist just trying to negate that would not be a real behavior for a scientist. What we usually do is that the hypothesis, scientists have a specific framework as a basis, and together with their rationale, scientists try to put it forward. So that's all I would like to say for now. Anything you'd like to add, Mehmet?
Yok, benim yok.
No, nothing I'd like to add.
There is another question for you, Thomas.
Okay, I hadn't seen that one. Would there be any advantages transferring evolutionary explanation to any other scientific domains, so economics, etc.? Well, I would say so, because I mean, evolution is a very powerful explanatory framework. It's a very powerful theory, and it basically explains the existence and the properties of complex organized systems. And given the fact that you find those systems in the living world, so in biology, but you also find them in economics and in social contexts. So basically our entire social world consists of all kinds of very complex and functionally organized systems that are not designed. So social institutions like companies, in part, of course, they are designed, but much of it, once a company is there, it starts leading a life of its own, basically. So there's a lot to explain there, and potentially, not necessarily, but potentially evolutionary theory can do a lot of work there. So I'm quite positive about taking theories from one area of work and trying to apply them in a completely different area if the explananda or the phenomena that you want to explain are sufficiently similar. Because you've got the framework, so you might as well see whether it works. But of course, there's no guarantee that it works. So this is part of the philosophical project to figure out under which conditions theory transfer from one area to another area could work. What are general conditions? And part of that is what I presented. So trying to figure out what kind of explanations do you build? And if you have an account of the explanations that you build in evolutionary biology, then you can see, is it at all possible to construct similar explanations in the area of economics? Or is there something fundamentally missing so that it won't work? So part of the project is to explore the conditions under which such transfers are possible. But I think it's totally advantageous because, I mean, it might work, who knows? And that's a great thing if you have a theory that applies to multiple different areas of reality. I think it's wonderful if it works.
Okay. I don't see any other question. So if the speakers have questions for each other, please go ahead. All right.
I only have a remark because, and this is to you, Mehmet. I don't think that we actually disagree that much, because I mean, what I was trying to do is to say, well, you've in biology and also in other evolutionary sciences, you have the process part and you've got the historical part, and what you talked about was just the process part. So I don't think that your analysis is completely right, but that's a different thing. But if your analysis is completely right, then that doesn't really affect my work because it all fits in the process part. And in addition to that, you've got the historical part. Okay. So I think your analysis and my analysis would fit quite well together.
I just thought that when I had this premise that the necessary condition for science to be autonomous is that it has its own non-reducible laws. So that part may conflict with this historical explanation.
Yeah, indeed, the historical part, of course, those are not there. There are no laws there, but you can still have laws in the process part. For my part, I'm not really sure whether you can say that the principles of Darwinism, so the core principles of evolution, for instance, if you take the 3 principles of Lewontin, I'm not really sure whether you can think of them as the laws of nature, but it might. And if you do think of them as laws of nature, then that would be where the irreducible laws are located. But in addition, you still need the history. That would be my take on it.
Yeah. Okay. Any other comments or questions? Because we don't have any question in the Q&A part. And if not, of course, we will end the panel here.
It's been a long panel, so.
Okay. All right. Thank you all. Thank you
for virtually having me in Mula. It was fun.
Now we always plan you to come here for a visit, but that never realized. So,
At some point, I'm sure at some point.
all right. Okay, I think teknik ekip mi şey yapacak, sonlandıracak, biz mi?
So will the technical team turn this off? By the way, thank you very much for hosting us. This was
Thank
quite
you
a
for
fruitful
the
discussion for us.
participation. We
Quite a
can
good panel
join
discussion from our side.
It's okay.
Thank you very much.
Yeah.
My regards to all of you. Thank you. I agree. This was a very useful, fruitful